Hello. Well, I've been given a call by a student and they've asked me to look at the problem I gave out in lecture 2.5 and 2.4 about the bias current problem. So I thought I'd work this one out in paper for you, and then you can follow it through in your own time on the video. So we've got in front of us the circuit here, but for the analysis I'll just redraw this on this page here. So we have a non-inverting amplifier here. It's connected to a 200 k ohm resistor here, and a signal source which is connected to ground. On the inverting input we have got two feedback resistors here and here, and the series resistor here Rx. The top feedback resistor is 12 k ohms and the bottom feedback resistor is 10 k ohms, and we have an output. And the question one is, what is the value of Rx? This value here. We know from the notes, for cancellation of bias currents, voltage from feedback node must equal voltage from non-inverting node, must equal voltage at non-inverting node. In other words, this voltage here and this voltage here must be the same for the amplifier to operate correctly. From this amplifier, since IB non-inverting must equal IB inverting, because we're not talking about offset currents here at all. Therefore, same resistance must be present at both nodes. Since R non-inverting equals 200 k ohms, from this resistor up here, therefore R inverting must equal 200 k ohms. Therefore R non-inverting, which equals 200 k ohms, must equal Rx plus, using superposition theorem, the parallel combination of 12k in parallel with 10k. Therefore Rx equals 200k minus 12k in parallel with 10k, which equals 5.45 k ohms, which means that Rx must equal 194.54 k ohms. And if we have Rx equal to 194.54 k ohms plus the parallel combination of 12k in parallel with 10k, which is about 5.454 k ohms, that would give us a total resistance in the non-inverting input of 200 k ohms, and we would land up with no offset output at the output of the amplifier, because the offset voltages due to bias currents in this path here would equal the voltage drop from this path here, which is basically the IB flowing through the 200 k ohms. So that gets the answer for part A. In part B, we're kind of asked the same question, but we're asked it in a different form. So in part B, here, IB equals 120 nanoamps. And Rx equals 200 k ohms. The question we have is, what is the voltage at the output, which is due to IB? We know that the input on the non-inverting input is 200 k ohms, so V of non-inverting input equals 120 nanoamps times 200 k ohms, this one up here, which equals 24 millivolts. Now we don't know whether this is plus or minus because we don't know what direction IB is flowing in, but it's not important which way it is as long as we're consistent. So let's just assume it's plus 24 millivolts. For virtual earth, V inverting input must equal 24 millivolts too. In other words, these two input voltages must be the same for this amplifier to be operating in a correct and linear fashion. But R in the inverting or feedback now equals 200 k ohms plus 5.454 k ohms, which equals 205.45 k. And this increase of 545 is because we have decided that this resistor in this case is 200 k ohms from part B, and the 5.454 k ohms is the parallel combination of the two feedback resistors. If R at the inverting input equals 205.45 k ohms, then V equals 120 nanoamps times 205.45 k, which equals 24.654 millivolts. In other words, there's a delta V equal to 0.654 millivolts. And the only place that can come from, and this delta V is due to the additional voltage drop from the 120 microamps flowing in this path here, due to the 5.454 k ohms. If we consider what's actually happening in the circuit here, we have the output of the amplifier driving the 12k resistor, which is connected to the 10k resistor, and the common point here is connected to the RX, now called 200 k ohms, and we have a current flow here of 120 nanoamps due to the bias current of the amplifier up here. And we've got a similar 120 nanoamps in that direction from the source. The effect at this node here must be equal to our 0.654 millivolts, which can only be generated from the output of the amplifier. The gain of the amplifier equals 10k over 12k plus 10k, all to the minus 1, because I've worked out the feedback factor, so you take 1 over the feedback factor, assuming a high gain amplifier, which equals times 2.2. If VA equals 0.654 millivolts, then Vout equals 2.2 times 0.654 millivolts, which equals plus 1.4398 millivolts. So the result of the mismatch between of increasing Rx from 195 approximately to 200 k ohms would give you an offset voltage at the output of the amplifier of plus 1.4398 millivolts, demonstrating that you must cancel out the effect of I-bias currents in order to get a good answer from the overall circuit here. I hope that explains the problem, and if there's any questions you can drop me a note by email or leaving a post on the Moodle blogs page. Thank you very much.